Hey, what's up, guys? This is Cheng here. So today, let's take a look at 1371. Find the longest substring containing vowels in even count. So this one is a pretty interesting problem, actually. So given like a string s, right? Return the size of the longest substring containing each vowel an even number of times. Right? So you'll know that vowel is a, e, I, o, u. Okay. And basically, you need to return the longest substring that each of this number has an even appearances. Of course, 0 is also counted as an even number of times. For example, we have this string here, and the answer is 13 because with this string here, so E has appeared twice. I is also twice, 0 is also twice, and A and U are 0. That's why, everything is even, right? And example 2 here, right? So this one, it's this one, right? LEETC. Here, this one is because it's 5, because E and E, they're even, right? Now the others are 0. And this one, obviously, this one, BC, there's no like vowels in here. That's why, the entire string is satisfied. And the constraint is like this, right? Standard 10 to the power of 5, and S only contains lower English letters. So for this one, since we're getting the longest substring, right, and most likely it's going to be a sliding window problem, and that's also what I tried to do at the beginning. Basically, I was trying to use a sliding window algorithm. Maybe, we try to expand the sliding window whenever we reach like a point that some condition doesn't match, then we shrink the left, right? That's how the sliding window works. But this one, after spending quite some time trying to figure out a sliding window algorithm, I figured that, this one cannot be solved by a sliding window because, since we need to check the parity, right, for all the 5 vowels here. For example, if we have like some strings here, let's say the left pointing to here, okay, and the right is somewhere here, we cannot, there's not like a clear condition that, it tells you, okay, now it's time to shrink the left pointer, because if we keep moving the right pointer, we might get a longer string, right? Because, depending on what's after the right pointer, we could have like another longer string that satisfies this kind of condition. That's why, this one cannot be solved, right? Because, let's say between the L and R, right? Between L and R, there are like 3 E's, right? This one is like it's not a valid it's not like a valid string, right? Then if in the normal like sliding window algorithm, it's time for us to shrink the left pointer. But in this case, there could be like another E later on, right? That's why, we shouldn't shrink L. Instead, we should keep moving R, right? That's why, we cannot solve it with sliding window. And then I look at this constraints, right? Obviously, we cannot use a brute force. Given like a a place, we simply just cannot check all the substrings. For this one, that will be a n squared solution, right? And it will TLE. So if we want to make some improvements and to pass these constraints, right, we either have to find like either use like a priority queue or a hash map to help us to quickly find the answers at each of the index. And then that's when I remembered there is like a very classic problem that I have solved so many times, which is called the longest subarray whose sum equals to k. Oh, and one more thing. So, like I said, we can either use like priority queue or a hash map to help us decrease the complexity to look for the best answers, right, for this index. But in this problem, the priority queue will not help us because the priority queue always usually give us like either the smallest or the biggest, right? But for this problem, all we care is the parity, right? It doesn't really matter like what's the count for each of the number here. We don't know. We don't know the answer for like a certain count numbers. All we care is the parity, if it's even or odd. That's why we cannot use the priority queue here. And then the last option for us is the hash map. Okay, and then go back to my previous topic. That's when I remembered there's a problem I solved many times, right? Basically, given like a subarray, right, and the target k, you need to find the longest subarray whose sum is k. Okay, so if you guys remember that, right, we have some numbers here, right? And given like an sum equals to, let's say, for example, 10. So how did we solve that problem? We maintain like a running sum, okay? And at each of the location, right? Let's say, for example, we're at here. We calculate the running sum, and then second time we have a target. Target equals the running sum minus k. Because that's our target running sum. Because if we have two running sum, right, and then the difference will be the subarray that we're looking for. And the third time we're having a hash map. So we have a hash map. The hash map where we store the smallest index for each of the running sum. And at each of the index here, we use the target, try to find if the target exists in this hash map. If it exists, right, and then we know we find a matching, we find a subarray. Let's say, for example, this is a subarray. Because here it will also have a running here it will have the target here, because if with the running sum subtract the target, we know what the subarray in between will have the target k. We'll have the sum equals to k. And the first one is that we only update, right? Only add, right, to the hash map will not exist. So this one is important because that's the way we can guarantee that for the same running sum, we only maintain the smallest one. Because let's say if the target is equal to 3, right, and the numbers could be like either positive or negative, right? Let's say that we have a 3 here, and then let's say somewhere in here we also have like a running sum equals to 3. But in this case, we don't update the index here, right? We only update the index. No, we only insert into the hash map when it's not there. That's the way we can guarantee that for given like a running sum, the hash map stores the smallest index for a given running sum. That's how we get the longest subarray. Okay, So that's a brief explanation for that problem. And then for this, and then we can just, if we can use a similar logic for the current one, that will be perfect, right? So now come back to our problem, right? So we have what? We have A, E, I, O, and U. So first, let's look at them one by one. So first, we need a running sum, which is the current state. So for this problem, it's a running sum. But for our problem, it's the what? It's a parity. It's a parity of this A, E, I, O, U. Like I said, the count doesn't really matter. All we care is the parity. It's either even or odd. Because let's say we have 2, 0, 6, 3, and 5. Okay, so let's say this is the current state. And now the second step is that we want to find the target, so that we can use the hash map to find the first target, right? So that we can get the longest substring in this case. Then what? But for our case, for our problem, then what's the target? Okay. If we maintain the count, the target could be what? So here you need to have like a good insight to be able to define this running sum and the target here. Because like I said, we're looking for a substring or a subarray, right? Who has like an even count for all 5 vowels. So what could be the possible ones? We have, it could be 2, right? It could be the 2, 0, 2, 1, 2, 1, 1, right? So if the previous state is this one, if the running sum is this one, and then if the target is this one, then 4 subtract 2, we have 2. So it's going to be 2, 0, 4, 2, 4. So this is a good one, right? But here we could have a different one. T could also be 0, 0, 0, and 1, 1. Right, so this one could also be a valid target, because this one, if you subtract this the running sum to this target, we also get like an even count for all of them. So that's why I said actually, the count doesn't really matter. So all we care is the parity for each of the vowels here. So either this one is either it's even, odd, or even. So this one is odd or even. This is odd or even. And if we can find a previous state, right, who has the same parity for all the 5 vowels, then that's gonna be the same one, because as you guys can see, so here these 2 are all a valid target, right? Why they're valid? Because their parity is the same as the current state. If the current one is is even, let's say for example, if the current one is 4, all we want to find is that if the previous one is also even, because even subtract even is equal to even. Same thing, odd subtract odd also equals to even. So now the problem comes down to, if we can find this, the same parity, right, for all 5 numbers, for all 5 pairs vowels. And since we only have 5 letters here, we can use a bit mask to store the parity for all 5s at the same time. So which means that we will have like 5 bit mask here, right? So 0 means even, and odd, and 1 means odd. At the beginning, everything is 0, which means it's 0. And every time when we have like when we see a different, like a vowel, let's say for example, if the current one is like a it's a E, right? So this one is E. Then okay, we know this one will become to 1 because we know now we have 1 E. And the second time we see another, like maybe an O here, right? And then we know, okay, so this one becomes to 1. And then the next one, if we see another E here, then we know, okay, so we have 2 E's here, which means all we need to do is just flip this bit value, right? As you guys can see, so the way we're maintaining this kind of bit mask is that every time when we have like a new vowel here, we can simply just flip the value, either from 0 to 1 or 1 to 0, because every time we add 1 count, the parity will be changed, right? So now everything's pretty much clear, right? So now we have a running sum, which is the current parity, and the target is the same parity, because like I said, with the same parity, if we do a subtract, right, and then what's in the middle will definitely have even counts for all 5 characters, letters, and that's pretty much it is. I think we can just then start coding then, right? Cool. So as long as we figure that out, everything left is just a coding. So first we need the length of this one, and then we need a running sum. In this case, it's like parity, right? So I'll call it parity. At the beginning, 0, because at the beginning everything is 0, right? So all 5 0. So 0 0 0 means 0. And then we have the answer equal to 0, and we have we also need this 5 vowels string here, A, E, I, O, U. Oh, and we also need a like hash map, right? So I use DP to represent the hash map because this one is like it has a DP concept in it, right? So for I dot C in the enumerate S, so here if the C is in vowels, right? If C is not vowels, then we simply just can ignore it. We need the index, right? Because since we use this A E I O U to represent the 5 letters, 5 vowels, right? And then we need to give each of them an index. That's how we do the flip, the bitwise flip. So I think in my case, I use this one. We have 5 zeros. I'm 8 here. So E I on U. So this is how I map this vowel into the bit mask here. So we have the index, and then going to be vowels dot index of C, right? So how do we flip the bit? There's a trick, right? So we simply do a XOR with this one. With the one left bit shift to the left by index times, right? Because I think I have already talked about this before. So let's say we have this one. If you want to flip this 0 to 1, right? If you want to flip this one 0 to 1, how do we do it? We simply do XOR with this one, 0 0 1 0 0, right? So XOR, this is going to be what? 0, right? So 0 1 XOR is 1 1 1 and 0, right? Similarly, if we want to flip this 1 to 0, right? We do the same thing. We do this one. We also do a flip of this one, and all the others are 0. If you want to flip this one to 0, right? Like I said, it's going to be 0 0 0 1 0, right? So that's just to remember, this is how we flip a bit value. And now we have this parity, right? So basically, if the parity is in, if the parity is in the hash map, okay, that's when we can update the answer, right? So the answer is going to be the max of the answer dot I minus, right, the dp of parity. And then we also need to update the hash map, right? So basically, if the actually, we can merge them all together, right? Since since in this case, the running sum and the target are the same, they're both parity. That's why we can merge them into one if else here. And then we have the parity else. We do a parity dp gonna be the parity equals to I, right? And then we return the answer. Yeah, so that's it. If I run the code here, this one accepted. If I run this one, 0, 0. Oh, I see. So this is a special case here. For in example 2 here, the answer is the string starting from the beginning. In this case, we need to put like 0 dot minus 1 here. So this one can help us handle this one, because the way it works is that we need if we have like this one. So this is the current I, right? So if we do a find like dp, if everything is from the beginning to current one, we need to do the I plus 1 in this case, right? I minus 1, which doesn't exist in the hash map. That's why we do initialize, we put a 0 and the minus 1 into it. If I submit, yeah, so now it passed, right? And yeah, so as you guys can see, the time complexity for this one is off n, right? Because we have hash map, and this one the index is the O of 5, which is a constant. Yeah, cool. I think that's it, right? As you guys can see, the code is pretty short, but the thinking process is pretty lengthy, right? Basically, we just to recap, right? So first we try to solve this one using sliding window, but it turns out that's not it's not possible. And then we're trying to see, given these constraints, we'll see if we can efficiently calculate the find the other side, because given like the right pointers, if we can efficiently find the left pointer, that'll be good, right? And then we have two options. We either use priority queue or the hash map, right? But the priority queue, since we're doing this parity thing here, and it's not useful. That's why we go to the hash map. And then for the hash map, we remembered, right? We have a similar problem that we have solved before, and we simply just need to convert this problem into that problem one way or the other. Okay, and then so the way we're converting is that we're maintaining like a running parity state. Okay, and in terms of the target, right, it turns out to be the same as the current parity, because same parity, if we do a subtract, will be sure to get like even number of counts for all the vowels. And there you go, and that's how we solve this problem. Yep, it's I think it's a pretty cool problem, and I hope you guys like the video, and I'll just stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.